This video is going to be talking about gas volumes. In the lesson, we looked at some ways of measuring gas volume. We need to be able to work with those measurements. Remember, now there is a rule, and that's the first thing we're going to talk about. We've got a rule for volumes of gas. At room temperature, and pressure, and these are standardized, so they're just set, room temperature and pressure, which can be abbreviated RTP. 1 mole of gas wants to be 24 decimeters cubed. That is a key volume, 24 decimeters cubed at room temperature and pressure. We can do calculations with that because that means number of moles equals volume, remember, in decimeters cubed, every time decimeters cubed divided by 24. That's just using this relationship. So if we had 24 decimeters cubed, that would be 1. 1 mole of gas is 24 decimeters cubed at room temperature and pressure. If you change one of these things, this volume changes. There is a law that governs that. We don't need to worry about that. And that holds for anything, whether it's a mole of atoms of helium, a mole of molecules of hydrogen, or a mole of molecules of methane. These would all be 24 decimeters cubed at room temperature and pressure. So it's all the same. Seems a bit weird, but gases behave a bit differently. We've got a lot of space between the molecules. So it's how they behave that matters, not how closely they'll pack together. Okay, so that's the rule, key rule that we need. Then the other bit we need to do is to be able to work with a graph. Now, a few things we need to know from the graph. First of all, if you're given a graph, it might look something like this, with time on the bottom, volume up the side, might be in centimeters cubed. Don't forget to convert if you need to. And we get a line, and the line will probably look something like this. Goes up quickly, tapers off, goes flat. Now, what can we tell from this? Well, if we read off here, that's the total volume. That's the maximum amount of gas there. That's the limit. That's how much gas is produced, no more, in total. Here, well, here really, the reaction has stopped because that is where the line flattens off. Here, the reaction is slowing down because we're using up our limiting reactant. And we can tell that because we've got a nice shallow curve. Here, we've got a steep curve. We're at the start of the reaction. That's where it's fastest. So, reaction starts fast, steep curve, slows down, shallow curve. Reaction stops, flat. That's our total volume. Now let's get rid of these labels as best we can, because we need to also be able to tell some other things. For instance, this has a limiting reactant. One of the reactants for whatever this reaction is going to run out and limit it to its maximum volume. If we were to reduce the amount of limiting reactant, we would have a reaction that would start off as fast and slow down at a lower volume. So that would be a lower maximum. Put max back up there as well. You see, smaller amount of reactant, so it's gone less far up the y-axis. Still started off the same speed, but has slowed down. And then finally, we need to talk about these curves. As I said, steep curve, fast